If you look back at the edge of a black hole, you'll see 100 versions of yourself. This isn't magic. It's the photon sphere. 15 seconds later, even light can't escape your eyes. Today we're tackling a brutal topic. What happens if you get thrown into a black hole? This time, it's not sci-fi. It's speculation grounded in hardcore physics. Before we throw you in, let's quickly review what a black hole actually is. Even Einstein back then described black holes as the place where God divides by zero. He didn't believe, not for a second, that something like this could truly exist in our universe. But look, humanity actually found them. When extremely massive, extremely dense stars reach the end of their lives, they undergo a huge transformation. They collapse in on themselves. Nothing is left behind. What they create is called a singularity, a mysterious point in space-time said to have infinite density and therefore infinite gravity. General relativity gave us a revolutionary idea. Gravity isn't a force acting on objects. It's space-time itself, curved by mass. That fully explains how Earth orbits the Sun and how the planets move as if circling their own home. Inside a black hole, there's no solid black surface. The singularity hidden within is simply too dense, warping space-time intensely, forming a deep well with nearly vertical walls. In 1939, Einstein himself even published a paper saying that stars collapsing into a singularity was unreliable and wouldn't happen in our universe. By coincidence, that very same year, the famous Oppenheimer, together with physicist Snyder, published a paper predicting that stars really could, under their own gravity, collapse into black holes. Now, let's talk about what happens if you get thrown into a black hole. Here's the wild part. Almost anything can become a black hole, whether you're a star, a planet, or a little person like us, as long as you're compressed into a region within your Schwarzschild radius. The German physicist Carl Schwarzschild was the first to find an exact solution to Einstein's field equations. The discovery was simple and beautiful. Take our sun, for example. If you compressed all its mass into a sphere with a radius of just 3 kilometers, boom, it would become a black hole. What about Earth? Earth would become a sphere with a radius of about 9 millimeters, roughly the size of a marble. If humans wanted to become black holes, that would be a disaster. We'd have to be compressed to something far smaller than a proton, unbelievably small. But if we really could become that small, then yes, we'd be a black hole. So which black hole should we throw you into? I think it's time to toss you into one, but which one should we choose? We could pick a smaller one, but that'd be boring. Let's pick a bigger one. Some black holes have event horizons larger than our entire solar system. That would mean billions of suns worth of mass, and that's a little too ridiculous. So let's choose one closer to home. Sagittarius A star, the supermassive black hole at the center of our Milky Way. You're orbiting it right now. It's also one of only 2 black holes humanity has ever directly imaged. Now let's set the scene. Suppose you and I fly there and park our spacecraft 1 trillion meters from the event horizon. We're going to send you down toward the black hole. As you free fall, I'll stay on the ship and watch. But here's the key. General relativity tells us that someone near a black hole may experience time completely differently from everyone else, because the black hole warps space-time so intensely. Interstellar showed this effect. To keep track of time, we'll give you a special watch. It can display, from your perspective and from my perspective on the ship, how much time has passed for each of us. We sync the watch, and you can begin your black hole journey. As soon as your journey begins, you'll see the distant black hole rapidly devouring matter. The scene is spectacular. Friction heats that matter to extremely high temperatures. If you tried to simulate this on an ordinary laptop computer, it would take more than 10 years. In reality, that disk would be bright blue or even white. But in this simulation, it's made orange, so it's easier for us to observe. The first time you check your watch, only 30 minutes have passed, and you've covered just 0.1% of the distance to the event horizon. So far, I'm only 11 seconds ahead of you on the ship. That time difference isn't too dramatic yet. Now we're closer to the black hole, and the curvature of space-time around it is creating all kinds of strange visual effects. Light coming from the side, even from behind the black hole, gets bent before it reaches your eyes. Let's check the time again. You've been gone for 2 hours, and you've completed 1.4% of the trip. And I'm now 44 seconds ahead of you on the ship. That time gap is a little worrying, but it's not totally outrageous yet. The black hole's shadow, the dark region in the middle, seems to be growing faster than we expected. That's because gravitational lensing bends light that would have passed right by you and redirects it onto your retina instead. After a long stretch of time, you finally check your watch again, and this time it gives us a scare. From your point of view, you left about 12 hours ago. But for me, on the ship, I've already been watching you drift toward the black hole for almost 15.5 hours. We're very close to the black hole now. Things are about to get very strange. Before you reach the point of no return, you'll arrive at a place that's both strange and wondrous. If you were frozen in time at this special place and looked around, what you'd see would absolutely shock you. You've reached the Photon sphere. This is one of the strangest places in the known universe. In the Photon sphere region, gravity is balanced just right, so photons can orbit the black hole. It's not that matter is emitting or reflecting the light. The photons themselves are trapped in orbit. If a beam of light moves tangent to the black hole, it can stay in orbit. But if its path changes even a tiny bit, the photon either falls into the black hole or flies off into space. Under these specific conditions, if you were simply frozen at the photon sphere and looked around, you would see a mirror image of yourself facing away from you. You'd see multiple copies of the back of your head staring out into space. You're actually looking at yourself as if you were standing right beside you. No real-time tech is needed at all. It's all the warping of space-time itself. As you continue your journey, you're getting very close to the event horizon. Now we've passed the photon sphere, and the black hole takes up more and more of your view. It feels like you're being swallowed by darkness, because that darkness is warping around you, revealing the back and sides of the shadow, and even parts that, in flat space-time, would normally be visible to you. You've been gone for 13 hours. In another 24 minutes, you'll cross the event horizon. But from the ship, I've already been watching your journey for nearly 20 hours. 18 minutes later, you check your watch again. Now I've been watching you for nearly 40 hours. For you, those final 18 minutes lasted a full 18 hours for me. The final moment has arrived. In another 6 minutes, you'll cross the black hole's event horizon. You close your eyes, take a deep breath, and check your watch. But it seems broken. It says I've been watching you fall for an infinite amount of time. But it isn't broken. Physics really is that astonishing. On the ship, I spend decades watching you slowly approach the event horizon until I finally see you become redshifted. That means I need an infrared telescope to see you. I can never see you cross the event horizon, even if I could live forever. For you, those final 6 minutes, for me, last forever on the ship. It sounds like science fiction, like a daydream, but it's absolutely real. It comes straight out of Einstein's equations. Now you're inside the event horizon. So what happens inside a black hole? Strangely, it's hard to tell exactly when you crossed the event horizon. You can still look out at the universe, see distant stars, and even see our ship floating in space. But all that light, just like you, has to race toward the singularity. You've passed the point of no return, that point of infinite density, where our laws of physics completely break down. Time itself comes to a stop. To escape the singularity's gravity, you'd have to go faster than light. We all know that's impossible. A common misconception is that if you look out at the universe, the extreme time dilation will let you see the universe's entire future, with history unfolding right before your eyes. But that isn't true at all, because the view doesn't work like that. As you approach the singularity, you'll see the outside universe compressed into a thin, narrow ring. In the end, when you get close enough to the singularity, your feet will be stretched out in front of you. And as your body spaghettifies, you're pulled longer and longer until you merge with the black hole. You drift together through the universe, forever. Just thinking about the whole process sends chills down your spine, yet you can't help wanting to see it for yourself. Black holes, these mysterious celestial objects, really make us both fascinated and terrified.